Okay, today we're looking at, from our Year 12 course, chapter on transformations of functions, transformations and graphs. We're going to start off by looking at the 6 types of transformation that we're going to be studying first off. We've got 2 translations, 2 reflections, and 2 stretches. At basic GCSE, you would have done 4 transformations all in all. You would have done translation, which is a shift, like that, slide around, reflection, rotation, and enlargement. Now, enlargement we're not doing as such because we're doing stretches in the x direction and stretches in the y direction. And roughly how it goes for y as a function of x. If the change appears in the bracket, it will change the x's and do the opposite of what you think, as we'll see here. So a translation of, say, 3 in the x direction will be written as f of x minus 3 in the bracket. Similarly, if it's a stretch, a translation of scale factor 2 in the x direction will be written as f of x over 2 in the bracket. So the bracket, it will do the opposite of what you think. Whereas any change in the y direction does exactly what it says on the tin. So if we're moving it up by 5, we write f of x plus 5 outside the bracket. If we want to double all the y's, we'll write y equals 2 lots of the function. So whatever it says is outside the bracket, changes the y's, does exactly what it says. If the change is inside the bracket, it'll change the x's and do the opposite of what it says. We've got to consider our 9 basic functions. Let's have a look at most of these now. We've got straight line, fx equals x. Your reciprocal function, fx equals 1 over x. Your sine curve, that's only part of a sine curve. Your y equals x squared, fx equals x squared. Your basic cubic, your cos curve, which is the sine curve just shifted. Your exponential curve, which is probably newish at this stage here. Equation of a circle, based on Pythagoras theorem, x squared plus y squared equals r squared. And the last of the trig ones, your tan curve, which has got asymptotes at 90 and 270 and so on. Right, let's have a look at some examples then. So let's consider y equals 1 over x. We're going to do a translation minus 4, 1. You want the equation and the sketch of it. Now, the translation minus 4 means that we're going to shove it back 4 in the x direction. For the function, what that will become on the bottom x plus 4, the opposite of it. What you've got to remember about a division line is it's a hidden bracket. We tend not to write the brackets there, but it's there. So that will become 1 over x plus 4. What does the plus 1 do there in the y direction? It just adds 1 onto the y. So that's what I mean about the change of x will be the opposite of what it says, x plus 4. The change of y does exactly what it says. And now if we consider the basic sketch of y equals 1 over x, like this, asymptote to the y-axis and the x-axis, what will happen in this case is it will shove it back by 4. So it will want to have an asymptote of the x is minus 4, and the plus 1 means it moves up by 1. So the curve will have asymptotes there, so y equals 1, and here, like that x is 4 and y equals 1. And at some stage or other, we could then go on and for our sketch, put more information on where it's crossing the x and the y-axis. There's my y, there's my x. If we consider this little function, y equals 2 root x, and its transformation y equals 2 root of x minus 5, it wants us to describe it. Well, yet again, a bit like the one before, the root part is a hidden bracket. So this is a change within the bracket. It's got x minus 5, so what it means is it's moving it 5 in the x direction. So it's a translation not changing the y at all, but the x, because that minus 5 does the opposite, so it's moving it 5 that way. And that's it, that's all it wanted. A couple of sketches and descriptions. It wants on the same set of axes y equals x minus 3 all squared and y equals minus x minus 3 all squared. So this is basically a y equals x squared type curve, but the first part is it's a translation in fact, because the minus 3 of 3 in the x direction. So it's the same basic shape, like this. That's y equals x squared. In this case here, what that will be, it will touch at 3 and like that. So there's my y, there's my x. I can stick x is 0 and get minus 3 all squared to tell me it crosses at 9. And then if I want to do y equals minus x minus 3 all squared, what's happening in this case is that y, for the second one, is always negative. There y is always positive, x minus 3 all squared, apart from x is 3. In this case, y is always negative apart from x is 3, so it will be a reflection in the x-axis, and this will cross at minus 9. So, description, reflection in x-axis, or in y equals 0. Similarly for our exponential curve, y equals 3 to the x and y equals 3 to the minus x, y equals 3 to the x, y equals anything to the x looks like that, goes up at an exponential rate, crosses with x is 0, 3 to 0 is equal to 1. I'll do it on a separate, even though it says do it on the same one, I'll do it on the separate one. Y equals 3 to the minus x, yet again, it's a hidden bracket, so it's actually like that, it's 3 to the power bracket minus x. So this is changing all the x values, and it's a rotation, doing the opposite of a rotation of 180 degrees is still a rotation. So it still matches what we said before, but it's going to look like this. And tying in with what's going on at the moment, I can rewrite this 3 to the minus x as 3 to the minus 1 to the x, or a third to the x. This number here, if it's bigger than 1 we have exponential growth, if it's between 0 and 1 we have exponential decay. And tying in with our r rate, for example, when r is bigger than 1, that's exponential growth. If r is below 1, we've got exponential decay, and that's what we're trying to achieve at the moment. And unfortunately, if it's bigger than 1, we're heading in the wrong direction, which is upwards like that. A few more examples, let's have a look at these. Y equals x cubed goes to what when we do a stretch of scale factor 4 in the y direction? Well, because it's in the y direction, it'll do exactly what it says, so it'll produce y equals 4x cubed. Nice, straightforward. Y equals sine x goes to y equals sine 2x. Description. Well, in this case, it's another hidden bracket. When you press sine, cos, tan on your calculator, the first thing your calculator does, it puts a bracket there. And in some cases, it will expect you, before it calculates it, to close the bracket there. Because it's sine of 2x. This 2 now is within the bracket. It's not doubling it or anything, but it's actually a stretch. Scale factor equals a half in the x direction. Okay, because that 2 there, it means there's actually concertina in it. We can get twice as many sine curves in the same range we had before. Instead of going from 0 to 360 as one cycle, we go to 0 to 180 and another 1 to 360. We get twice as many. Okay. Similarly, y equals x cubed and y equals x over 2 cubed. And what's happening in this case, if I was to do a sketch of y equals x cubed, like that, a sketch of y equals x over 2 cubed on the same one. There's y equals x cubed. The over 2 is stretching it by a scale factor of 2. It's within the bracket, so it's not halving the x's, it's doubling the x's. So it will look like that. That would be y equals x over 2 cubed. And as I say, it's a stretch, scale factor of 2 in the x direction. I could times the bracket out and write y equals x over 2 all cubed as y equals x cubed over 8, or an eighth of x cubed, and I could have described it as being a stretch scale factor 1/8 in the y direction. The idea is every y value, the dotted line should be an eighth of the value of y there, and similarly up here and so on. Okay, so it's not, there's not one single answer. There could be two answers for stretches. We could consider it being one the stretches in the x, one the stretches in the y. Okay, last couple of examples. We've got a cubic function of x, y equals x cubed plus 5x squared minus 3x plus 40. And we're asked to do this translation, 2, 3. So it means we're going to shove it along 2, and shove it up by 3, and he wants us to rewrite the new equation. Well, the new function becomes y equals f of x minus 2, because of the 2 there, and then plus 3 because of 3 in the y direction. What it means is that y will be, I replace x with x minus 2, so it becomes x minus 2 cubed plus 5 x minus 2 squared minus 3 x minus 2, and then plus 40 and 3, I'll probably write it as plus 43. I don't think they're expecting us to multiply it all out, but I wouldn't leave it as plus 40 plus 3. I think it's within our mathematical abilities to add 3 onto 40 for that one there. And last one, sketch. Even though I've written sketch, I'll try and write sketch there. Y equals 5 to the power x minus 2. For these curve sketching ones, it's probably worth doing several little sketches till you get to the final answer. So what I mean is this. We can do our first one, in this case y equals 5 to the x, there, and realise that that crosses the y-axis. When x is 0, 5 to the 0 is equal to 1, and then think that minus 2, because it's outside the bracket, will move the whole thing down by 2. So what I've got in this case is this. It'll have an asymptote now at y equals minus 2, and do that. It will cross there at minus 1, 2 lower than it was, and at that point there we don't yet know how to solve it. We'd have to solve 5 to the x is equal to 2 and then do that, and we haven't quite covered that in our course yet. So this is y equals 5 to the power x minus 2. If that minus 2 was within the power, well, that would be a shift in the x direction, and it would do the opposite. It would shove it all 2 that way. But in this case, because the minus 2 is outside the power, outside the bracket as it were, you move it down by 2, and that's our shift. So I wouldn't want to, when I'm doing multiple stage curve sketchings, go straight to the final answer. I'd have one, maybe a second, and maybe a third, depending on exactly what's going on, until I get to the final answer. And don't forget, I haven't said it so far, but curve sketching without numbers is artwork. This is maths, we need numbers on. So I've got my equation, the asymptote there, I've marked it, cross it at minus 1 there, and eventually we will solve where it crosses the x-axis, so I can put that on as well.